Hey there, everybody. Let's get started on section 4.5. We're doing derivatives and shapes of graphs. So previous we learned how the first derivative can help us identify where we have a local max or a local min. And now we're going to learn a little bit of an easier way to do it. I think it's a little bit easier way to determine if it's a local max, a local min, or if the critical point was neither. And we'll also see how this affects the graph. So not just where they're at, but how it affects it. We will take advantage of that third corollary of the mean value theorem. It showed us how to find regions of increase and decrease based on the first derivative. And so, like, regions of increase can come in two flavors. We can have it look something like this up top, where it's increasing but curved upwards. So it's curving up. Or we have regions where it's curving downward. So like if I did this, it looks like it's making a bull. Here it looks like it's making a bull, but the first derivative is positive there for both of them. Okay. And so there's a couple ways that this can fall out, and we'll take a look at it in a second. We could also have where it's negative, where it looks like a bull going downwards here. And this kind of looks like a bull going upwards here, but in both cases, f prime of x is decreasing. So you can see that right there. And that's talking about the first derivative there. It's kind of blurring that out. I think I'm going to get rid of those for this picture. Okay. And if we look at something like this, we can see how stuff's affected by it. If we take a look at how increasing and decreasing is affecting it, regions that are increasing look like that region. It looks like that region. And we skip over C, but right there. And we were decreasing here and here. And the spots where the derivative actually equaled 0 were right here. So it looks like we can see we've got a local max. We've got a local max right here and right there. Okay. And it looks like we have a local min here. But notice this one, even though we had a critical point there, we don't have a local max or min. So looking at increasing or decreasing and thinking of it in terms of that is helpful. And when I mean increasing or decreasing, I'm talking about the derivative is kind of increasing right there. Well, yeah. Derivative is either less than 0 or no, when I'm saying increasing or decreasing, I'm talking about the function. Sorry. We're going to look at the derivative increasing or decreasing in a second. Okay. That leads us to our first derivative test. We're going to let f of x be continuous on our interval I, and that interval will contain some critical point C. If f prime of x exists on I, like so if the derivative exists, if f of x is differentiable on the interval, except maybe at our point C, one of the following happens. If f prime of x is greater than 0 and for x less than c, and f prime of x is less than 0 for x greater than c, which happens right here and right there, it's increasing on the left and decreasing on the right, then we have a local max. So this is a way of seeing that without graphing it. And we'll look at it like this is the word way of doing it. We're going to show a nice little sign chart in a second that'll be perfect. If the derivative is decreasing before c and then increasing after c, we have something like this. It's going downward and then it's going upward. So we have a local min. Here, it was going upward and then it was going downward, so we had a local max. If f prime of x doesn't change signs around C, let's say it's going upward and then upward again, or downward and then downward again, we can see that we don't have a max or a min in between. So the way we take advantage of the first derivative test is we're going to find all the critical points of f of x. We're going to make a sign chart of regions where it's increasing and decreasing. And how we'll do that is we're going to draw a line with all the critical values of x marked, and we're going to be sure we include locations of discontinuities. And then we're going to find the sign of the derivative in each region. And then we're going to use that along with our first derivative test to identify local maxes and mins, kind of like I did up here with these purplish arrows. Okay? So our first example we're going to do is this problem right here. So f of x equals 1/3 x cubed minus 3x squared plus 8x minus 5. If I take the derivative, I have x squared minus 6x plus 8. So step 1 was find all the critical points. We find the critical points by setting it equal to 0. And when we do that, we find our critical values are at x equals 4 and x equals 2. Okay? And so our critical point will have a point at 2 comma f of 2. That's one critical point. And we'll have a critical point at 4 comma f of 4 as another critical point. But what we're going to really use is we're going to use our critical values here. Well, we're going to use this actual equation. This equation right here, this equation here, in fact, the factored form is what you want to use. We're going to use that down below on our sign chart. So what I do, I'm going to make a sign chart. And what I'm going to do is 2 and 4 were my critical values. I picked just 3 test points, or a test point in each region. 0 is always a great test point. Multiples of 10 are always really easy to do mathematically, so those are good test points. Sometimes if a fraction works well, like using a value where it cancels the fraction is pretty good. So what I'm going to do is I'm going to go into this first derivative right here, and I had x minus 4 and x minus 2. This is what I'm filling in right here. X minus 4 and x minus 2. What I want to know is the sign. So I've got 0 minus 4 times 0 minus 2. And I don't actually care if it's what the number is. This is negative, this is negative. So the overall region is positive, which means f of x is increasing on that graph. If I do the same thing with 3, I'm going to each time plug it into this right here. Plug into here. Okay. So when we do that, I've got 3 minus 4, 3 minus 2. That's negative 1 times 1. That actually ends up being a negative number, which means f of x is decreasing along here. And when I do 10 minus 4 and 10 minus 2, this 10 minus 4 is positive, 10 minus 2 is positive. 2 positives make a positive. It's increasing here. So we can see at x equals 2, like if we did like a little rolling hill kind of thing. It's going upwards here, and then when it gets to 2, it starts going downwards. And when it gets to 4, it starts going upwards again. Okay? So it looks like we've got a local max at 2 and a local min at 4. And I went and figured out what those two values were. We will use them down below, but for now, just plug these values in here rather than rewriting the notes and stuff. X equals 2, it's going, and the reason why, notice it's going from an increase to a decrease. The derivative changed signs. So increase to decrease is a max. And if you do the arrows and making it look like it's going up, so it's increasing, and it's going down, so it's decreasing, I think it's really easy to spot that this is a max. It's making a hill right there. That's a little hill. And when it's going from decreasing to increasing like it is at 4, we've got a little valley right here. It's going like that. So it's got a bottom right there. Okay? So I'm going to make another video and have you guys try a couple problems. Let's come over and stop recording.